This is a demonstration video of the tool jPET, an automatic test case generator for Java programs. jPET can be used within the Eclipse integrated development environment as a plugin. For more information, go to the eclipse.org web. So let us start Eclipse. Well, regarding the installation, jPET can be easily installed in Eclipse via an update site as any other Eclipse plugin. For this, we go to Help, Install New Software. Once here, we specify an update site where the plugin to be installed is located. The jPET Eclipse plugin is available at this URL, so we write it here, press OK. We see now jPET in this box. We select it, including all its features, press Next, and just follow the steps. When the process finishes, we restart Eclipse and jPET will be ready to be used. As we can see, Eclipse now shows the jPET menu bar and the little dog icon in the toolbar. Before using jPET, we must activate the jPET view. This is done by going to Window, Show View, Other, and then selecting the jPET view and pressing OK. Let us consider the following simple example to illustrate the presentation. This is a class for representing sorted lists of integers implemented as singly linked lists ending with a null pointer. Class SLNode implements the nodes which contain an integer and a pointer to the next node in the list. Let us focus on method merge. This method is supposed to merge the actual list with the list provided as argument, so that the actual list after its execution points to a sorted list containing the data of both lists. Also, the method is supposed not to create any new node and therefore generate the new list just by setting the next pointers of the nodes in the appropriate way. Let us now tell jPET to generate a set of test cases for method merge. For this, we first select in the outline view the method for which we want jPET to generate test cases, in this case method merge, and then we click on the jPET icon. We now see a window where we can select the preferences of jPET. The first one specifies the coverage criterion. Let us select block K and K equal 2. For more details on this, you can have a look at the jPET website, and in particular the papers describing the symbolic execution engine of jPET. Intuitively, setting the option this way means that jPET will generate test cases for covering all feasible paths in the program, limiting the number of iterations or loops to 1. Second option allows specifying whether we want to get concrete, that is to say numeric test cases, or just get path constraints. We select concrete and select the domain of integer values to 0 to 10. Let us let the rest of the preferences with their default values and then click Generate. The jPET view shows the test cases that have been obtained in a tree-like structure organized in packages, classes, and methods. We navigate and select the test cases for method merge. We can see that jPET has generated 9 test cases. For each of them, we can see its input and output arguments, and also whether the execution ended normally or with an uncaught exception. Let us observe the last 3 test cases, which, as we can see, are exercising executions ending with an uncaught exception. In the last one, we can directly see that the exception is produced when the input argument is a null reference. In general, in order to understand what is going on, we will need to observe the contents of the objects transitively pointed to by the references in the input and output arguments. The jPET test viewer allows us inspecting such information. It is opened by double-clicking on a test case. Let us inspect test case number 7, so we double-click over it, and we can now see the test case viewer window. On the right, we can see the information of the test case, including a table representation of the input and output heaps together with the contents of the selected object. On the left, we can see a tree-like graphical representation of all reachable objects from the selected one. By default, the viewer shows the tree starting from each input argument of reference type. Note that objects are labeled with the reference name they are pointed from. Now, clicking on object B, we can see that its field first has a null pointer, which denotes that the list is empty. This is probably revealing a bad behavior of the program, namely, a null pointer exception is being thrown if either one of the lists is empty or the input argument is null. In the 3 test cases, we can actually observe there is a null pointer exception object in the output heap. The other 6 test cases correspond to all feasible combinations of decisions in each branching of the code, allowing 1 loop iteration. Interestingly, jPET is capable of showing the trace of instructions that are exercised by a test case. This is done by right-clicking on a test case and then pressing Show Trace. Let us inspect test case 1. The footprints on the code show the numeric sequence of exercised instructions. We can see it exercises the first else branch, it goes into the loop body exercising the else branch inside. It goes out of the loop and finally exercises the last else branch. Such an execution corresponds to the case in which the first two elements of list L are smaller than the first element of the this list. Let us observe this in the test case viewer. We can also see that in the output, reference A is pointing to a list that contains all data, and furthermore, that no new objects have been created, just the corresponding pointers have been set accordingly. jPET yields additional information in the console window, depending on the verbosity level. In particular, we can see the code coverage statistics. Observe that for this concrete example, the set of test cases obtained are exercising the 100% of the code. Let us now run again jPET for method merge, but this time we enable the option references aliasing. We now get 16 test cases. A first look reveals that some of them correspond to the merging of a list with itself, a case that the programmer might not have considered. Let us inspect test case 1. We see that the list with one node is indeed being merged with itself. The result is a cyclic list, which is something that should be probably avoided. Another useful functionality of jPET is the possibility to write method preconditions by means of YML annotations. YML is the most commonly used specification language for Java. So let us write an annotation saying, for example, that lists to be merged are not the same. If we call jPET again with references aliasing enabled, we now get 13 test cases. A careful inspection, for example at test case 2, reveals that even if the lists are not the same, some nodes within them can be aliased, in which case a cyclic list is still obtained as output. This again reveals a dangerous behavior of the program. An interesting observation is that jPET do not use the Java source code for the generation of the test cases, but rather it uses the Java bytecode, that is to say the .class files. In the example we have seen, the test cases have been obtained actually from the bytecode that Eclipse compiled from the Java source code. This means that we can have the same capabilities we have shown also for Java bytecode programs for which the source is not necessarily available. This could be very useful from the point of view of reverse engineering. In particular, this allows program comprehension of Java bytecode programs by means of observing the behavior of a set of concrete executions. For instance, a set that covers all feasible paths allowing k iterations of the loops. Well, so that was a demonstration of the basic capabilities of jPET. For more information, you can go to the PET project website at http://costa.ls.fi.upm.es/pet.